Okay. First, in the interest of simultaneously moving things along, but also buying Walker a little more time to get here, um, do either of you have any questions on any homework problems I put out there, since I put one out there last time?
I do not have a specific question right now. I feel like I should, but I don't. I just feel like I'm not there yet. I'm still kind of overwhelmed by all my assignments right now. I'm trying to figure out which one to even tackle first, but
Oh, okay. So you haven't really gotten into it yet.
I'll get there soon.
Okay. And are you referring to a problem I just put out there last time?
Um, no, I haven't even,
Oh, the first one.
yeah.
Okay. All right. And okay. And thank you for corroborating that, Taylor. Um, so, all right. Well, dang. Now I feel bad because I've had in mind to put out another problem. Um, uh, After what I covered today. Although I really don't care when these are done. Um, so I
Do what you gotta do, but I'm just trying to figure out now that like I'm in 721 too. I'm just trying to
right.
what to
Yeah.
prioritize first.
Yeah. Okay. Okay. Well, for that, what I would suggest is make 721 a higher priority, because it's already laid out. Like, here's what the work is for the semester, and actually, it says, as you just heard me in that class, that next week is going to be all about homework and making sure that people are in good shape there, and that'll be a chance to get a lot of help if anything. If um, I would encourage you to at least do what you can, at least to be familiar with what's required for the first two problems, let's say, because those are a pain, and then 3 and 4 should be uh, um, reasonable after that. Um, okay, here's Walker. Cool. Um, and because for this class, it actually I was struggling from the beginning, like, okay, what will I give you all for homework? Because like I know what I want to cover, but there's certain things like, well, I'd rather just cover it than make a homework problem out of it. Um, if I've covered something, and then okay, now we make this little change, and now you guys carry that out using, that works. But there's only so many situations like that. So, but it is helpful for me to know how you all are doing, because that helps me calibrate the class. Like, because I don't want this class to be, the straw that breaks three camels' backs. And uh, yeah, so in other words, what that means in practical terms is, okay, yeah, I have in mind what the next problem will be, but if I have trouble thinking of anything to give after that, I'm not going to worry about it. Um, so, um, and y'all are going to be busy anyway. Um, okay. Yeah. Well, plus you have, um, well, yeah, all three of you have 560 to deal with also. So, okay. Um, whew, oh God, like the suffering I'm inflicting. Okay. All right. Um, okay. But at least, because it's 3 classes of mine, then that allows me to be flexible. Um, okay. So what I'm going to do, I have one specific ODE that I want to focus on. We'll see how far I get with it, and if because it's really all I'm prepared to do anyway, um, and we'll see how this goes, because pretty much most of this class has been me winging it. Okay, so All right, so the problem we're going to look at is the typical second order ODE, homogeneous. Okay, actually, do I want to make it that way? Yeah, for now, I'll just leave it homogeneous. And then I will throw in some initial conditions. Okay. Okay, are constants. Okay. Now, so falling back on what I've been covering. Okay. Sorry, one second here. All right. So I'm going to let u1 equal to y, u2 equal to y prime. All right. All right, so u1 prime equals u2, and then u2 prime, which is y double prime, that'll be equal to minus p. So these terms get moved to the other side. Minus p y prime, but y prime is u2. And then I have minus qy, but that's u1. Okay. And then we have, okay, y, or u1 of 0 is y naught. u2 of 0 is y prime of 0, but that's z naught. Okay. Now, I want to rewrite this system in matrix vector form. Okay, so for that, I just need to set the notation. All right, so I'll just find U to be a vector consisting of U1, U2. And I'm going to define the matrix A array. So whatever's multiplying the U's will go in here. So I'll go have the first row 0 because there's no U1 term, and then 1. And then down below I have minus Q and minus P. Okay. So now we just have U prime is equal to AU. Okay. With U of 0, all right, for initial conditions, that's U naught. Okay. All right, so we have Y naught, Z naught. Okay. Now, in some form, we know what the solution is from what I've covered recently. Okay. least for this first order system, so u of t is equal to e to the at u naught. So the goal for today is we want to work with this form of a solution to get a solution formula for y of t. So really, even though our solution is a vector quantity that includes both y of t and y prime of t, we just want to extract the first component of this and express the solution in using notation that only comes from here. Because here we've changed the problem into a first order system, blah, 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 but we want to describe it in these terms. Okay, so that requires getting an expression for e to the at for this matrix. Now, on the one hand, what I could do is I could take this A and use the Taylor series, like identity plus A t plus 1/2 at squared and so forth. But to work out these powers, that would be that'd be too much. So if we're just focusing on e to the at, it's Jordan form. So if A can be factored into xjx inverse, and J is a Jordan form, which, as we saw before, is a block diagonal then, as we saw before, e to the at is equal to x e to the jt x inverse. And certainly e to the jt would be a whole lot easier to compute than e to the at because it's block diagonal. So we can take the exponential of each block. And then, but to do this, we need x and j. So we need the eigenvalues, eigenvectors, and generalized eigenvectors, if any, of A. So if we can just get those, then we can do all of this. All right. Now, are any questions up to, whoops. Questions up to this point, Okay. All right. Oh, it's weird how it says, oh, okay, it says this for all of you. Like, for instance, Taylor Bedell has temporarily joined the chat. I wonder how it decides whether it's temporary or not. I guess it's temporary for all of us, but anyway, that just struck me as odd. Is that like a temporary profile picture in Facebook or something? Or I don't know. Okay. Anyhow, and fortunately, this will be easier to do because we're only dealing with a 2x2 matrix. Okay. The eigenvalues of A are the roots of its characteristic polynomial. Also, hold on. Yes?
Oh, hey, how are you?
Good, how are you?
I'm just fine. I'm Reynolds Bodenhammer. I'm one of the adjuncts here.
Oh, okay.
Office hour schedule right now.
Oh, you did? Oh, shoot.
Yeah.
Okay. I'm sorry. I have I'm a Hattiesburg faculty member, and I have a class that's video conferenced here, and so I asked my colleagues down here, like, where can I teach virtually?
Gotcha.
And so they sent me here. So
I mean, so far I am 0 for, 0 for a million as far as like people that have actually popped in.
okay.
What I'll do, I'll just like set up somewhere and.
Okay. I'm only going to be here for 25 more minutes.
Okay, if somebody swings by, then, I'm gonna keep you around here.
Okay. All right. Sorry about that. Okay.
No worries.
All right. Thank you. Oh, dang it. Well, that was awkward as hell. um, okay. Let's get this over with. All right. So all right. The sum of the roots or some of the eigenvalues is the dang it. I hate when it does this. I know you're all used to hear me grumble about this program, but sorry, not sorry. Okay, let's try this again. The trace of A denoted by that, which is the sum of the diagonal entries, and the product of the eigenvalues is the determinant of A. Therefore, if you have the eigenvalues lambda 1 and lambda 2, we have the following. Here's the trace, is the sum of diagonal entries, that would be minus P. And then the determinant would be Q. So we have these relationships. Lambda 1 plus lambda 2 is equal to minus P, and lambda 1 times lambda 2 is equal to Q. All right. Okay, so now all right. So what I'm going to do is forgive for doing this on the fly. I can multiply the first equation by lambda 1. What that gives me is lambda 1 squared plus lambda 1 lambda 2 is equal to minus P lambda 1 but lambda 1 lambda 2 is equal to Q, so I have lambda 1 squared plus P lambda 1 plus Q is equal to 0. I can do the same thing, multiply by lambda 2, and I get lambda 2 squared plus P lambda 2 plus Q is equal to 0. So in other words, lambda 1 and lambda 2 are roots of this quadratic. Which is a characteristic equation of the ODE, as the terminology from a first ODE class. Characteristic equation lambda squared plus p lambda plus q is equal to 0. This is also what you would get if you were to compute A minus lambda identity for the characteristic polynomial of A. All right. Now, okay, so we're getting the eigenvalues of A. We're going to assume that the eigenvalues at 1 and lambda 2 are real and distinct. So there are three possibilities: real and distinct, real and equal, also double root, or they are complex roots. So for now, I'm just only going to do this one case. So what are the eigenvectors of A in terms of these eigenvalues? So the eigenvectors, I will call them, stop it. X1 and X2. So to satisfy this equation, AXI is equal to lambda I XI. Okay, so how do we actually solve that? So if I write this out element by element, all right, so actually I'm going to rearrange this. So that equal to the 0 vector. All right. So a matrix will be minus lambda I, the 1, 1 entry, and then I have a 1. And then the second row I have minus Q, and then minus P minus lambda I. And then my unknowns, my eigenvector, so that would be x1i, x2i, and that equals 0. Okay. Now the thing is, the lambdas are such that this matrix is a singular matrix. That means, so when a matrix like that is singular, that means that an equation can be expressed as a linear combination of the other equations. But here we only have two equations. So when you have a 2 by 2 matrix that is singular, that means that either one of the equations, all the coefficients are 0, which is not what we have here, or it's a situation where one equation is a scalar multiple of the other equation. So we really only have one independent equation. So we can solve one of these equations for the x's, and the other equation would produce the same result, just a scalar multiple of it. But remember, any eigenvector, any scalar multiple of an eigenvector that's non-zero is also an eigenvector. So we're going to have infinitely many solutions anyways. So we might as well just solve a simpler equation, this first one. So what we have is lambda I x1i plus x2i, and yep, I forgot a minus, is equal to 0. So what I could do is I can pick one of these entries and solve for the other one. Like I'll pick a first entry equal to 1. So the eigenvalue, the eigenvector for lambda I is so first entry is a 1. Like if I set this equal to 1, but the second entry is just going to be the eigenvalue. So that is xi. And because the two eigenvalues are not equal, then these eigenvectors are known to be linearly independent. Because to be linearly dependent, the two eigenvectors would have to be scalar multiples of each other, but that's not going to happen because we have a 1 and a different numbers down here. So in this case, it's diagonalizable. So anytime you have a matrix where all the eigenvalues are distinct, then you know if a matrix is diagonalizable in that case. So our factorization is xjx inverse. So now we can pretty much write out what that is. So in X, these are the columns of capital X. So 1's in the first row, and then the two distinct eigenvalues in the second row. Okay. And then the diagonal matrix consisting of the eigenvalues whoops. Okay. And then the inverse of this matrix is what would go over here. Now, to get the inverse of a matrix, for a 2 by 2, you take 1 over the determinant. The determinant is lambda 2 minus lambda 1. So I'm just going to put that out front. Okay. Then, to get the elements of the inverse, okay, so first I'll just copy it over there. What you do is you swap the diagonal entries. So I'll put a lambda 2 up here and a 1 down here. And then you negate the off diagonal entries. So I'll put a minus here and a minus here. Okay. I'm doing a very quick verify, but this is the inverse thing in my head. Yeah, okay. So now we have a factorization. And earlier I had written that the exponential will just be x itself, exponentiate the Jordan form, and then multiply by x inverse. So now I can do that down here. So e to the at would be x times e to the jt x inverse. So I just have to multiply this middle one by t and take the exponential. So I have e to the lambda 1t, and then e to the lambda 2t. Okay. All right. Okay. Questions up to this point? Okay. You understand. Okay. Now, so really want y of t, but that is the first component. Take a first component of a column vector, you multiply by E1 transpose. That's the first column of identity. Times u of t, but u of t is equal to e to the at u naught. But now we have e to the at x e to the jt x inverse times u naught. Okay. So I take my initial vector of initial conditions, y naught, z naught, multiply by this matrix, then this matrix, then this matrix. But then I'm only taking the first component of what I get from here. Okay. All right. All right, so y of t. So since everything I'm dealing with here is 2 by 2, E1 is just, so first row of a 2 by 2 identity matrix, which is just a vector. Whoops, how'd that happen? Oh, okay. 1, 0 times all of this. So I need to bring all that in here. Okay. And then I also need the vector of initial values. Here we go. All right. So this is the solution. It's just that there's all this matrix multiplication to do. And let's see, I don't have much time, but I'll do what I can. So for one thing, okay, that scaling factor of lambda 2 minus lambda 1 is why I have to assume that the roots are distinct. So I know I'm not going to be dividing by 0. So I'm just going to put that up front. Oh, not there. I want to do it in the second row. Okay. Okay. Now, here, when I multiply this by this, all this is doing is saying take the first row. Well, so then I'll just have this 1, 1 here. So that's gonna this product is just going to be the vector 1, 1. Okay. Okay. Notice this is a diagonal matrix. When you multiply something on the right by a diagonal matrix, it has the effect of scaling the columns. In other words, the first column is scaled by this element. The second column is scaled by this diagonal element. Okay, I was thinking of a major LaTeX error somewhere, but okay. So, so I can condense this even further. So this 1 is going to be multiplied by e to the lambda 1t, and the second one will be multiplied by e to the lambda 2t. Okay, and then that diagonal matrix goes away. Okay. So those matrix multiplications were could be simplified, but no more. This one actually has to be carried out in full. So that would be lambda 2 y naught minus z naught. Okay. And then the other entry would be z naught minus lambda 1 y naught. Okay. Okay. So then this matrix goes away. Okay. So now we have a row vector times a column vector. Well, that's just a that's just a dot product. So what we end up with finally is okay. So y2, okay, I'll do it this way. I'll have two fractions of this form. Okay, so I'll have this as a numerator for the first one, and this as numerator for the second one. Okay, and the first one is times e to the lambda 1t, and the second one is times e to the lambda 2t. Okay, so that's y of t. And to confirm, like e to the lambda 1t and e to the lambda 2t are solutions of the underlying ODE. All solutions are linear combinations of these functions. So that's why, it satisfies the ODE itself, which is linear. To make sure it satisfies the additional conditions, like if you said t equals 0, then you add these two terms together. So the exponentials become 1, and you have minus z naught plus z naught. Those would cancel out. And then I'd have lambda 2 minus lambda 1 times y naught. The lambda 2 minus lambda 1s would cancel, and you're left with y naught. Similarly, if you took the derivative of this with respect to t, this term fraction would be multiplied by lambda 1, and this fraction would be multiplied by lambda 2, and the y naught terms would end up canceling out, and then you'd have a cancellation of like with this denominator, and you wind up with z naught. So it can be verified that this solution satisfies the ODE and the initial conditions. Okay. Other questions? This is probably the last homework problem I'll sign for a while. What solution y of t if the roots are complex, meaning they're equal to alpha plus or minus I beta. So they're still distinct. So the devs still have two literally dependent eigenvectors. A lot of this will work out the same except being complex. But the solution is supposed to be real. But you can have sines and cosines. And if alpha is not equal to 0, you also have exponentials. So I want to arrive at a formula: y of t equals something that satisfies the initial conditions. But like if you could start with this, it's just that it would be complex. So then you would take into account that lambda 1, lambda 2 are complex conjugates of each other. Like you should express those in terms of alpha and beta. And express these exponentials in terms of alpha and beta also, and then use sines and cosines to cause any imaginary parts to cancel out. All right. And now I can let this guy have his office back.
That the sines and cosine, is that where I'm trying to recall correctly? Like, it's usually I is attached to sine.
So what you're using is
It's,
e to the I theta equals cosine theta plus I sine theta.
okay, that's what I thought. Okay, I was just making sure.
Yeah. Okay. Other questions? Okay, well, I can see you all in half an hour anyway.